Analyzing the data. The learning objectives for this section are: 1. Distinguish between descriptive and inferential statistics. 2. Identify the different kinds of descriptive statistics researchers use to summarize their data. 3. Describe the purpose of inferential statistics. And 4. Distinguish between type 1 and type 2 errors. Once the study is complete and observations have been made and recorded, the researchers need to analyze the data and draw their conclusions. Typically, data are analyzed using both descriptive and inferential statistics. Descriptive statistics are used to summarize the data, and inferential statistics are used to generalize the results from the sample to the population. In turn, inferential statistics are used to make conclusions about whether or not a theory has been supported, refuted, or requires modification. Descriptive statistics are used to organize or summarize a set of data. Examples include percentages, measures of central tendency, like the mean, median, or mode, measures of dispersion or variability, like the range, standard deviation, or variance, and correlation coefficients. Measures of central tendency are used to describe the typical, average, and center of a distribution of scores. The mode is the most frequently occurring score in a distribution. The median is the midpoint of a distribution of scores, and the mean is the average of a distribution of scores. Measures of dispersion, also called spread or variability, are also considered descriptive statistics. They're used to describe the degree of spread in a set of scores. So are all the scores similar and clustered around the mean? Or is there a lot of variability in the scores? The range is a measure of dispersion that measures the distance between the highest and lowest scores in a distribution. The standard deviation is a more sophisticated measure of dispersion that measures the average distance of scores from the mean. The variance is just the standard deviation squared. So it also measures the distance of scores from the mean, but in a different unit of measure. Typically, means and standard deviations are computed for experimental research studies in which an independent variable was manipulated to produce two or more groups, and a dependent variable was measured quantitatively. The means from each experimental group or condition are calculated separately and then compared to see if they're different. So what does the standard deviation tell us in more layman's terms? Roughly speaking, the standard deviation is the average distance of the data points from the mean. When you have a low standard deviation, that means the data are tightly packed around the mean. If you have a high standard deviation, that means the data are more spread out around the mean. For non-experimental research, simple percentages may be computed to describe the percentage of people who engage in some behavior or held some belief. But more commonly, non-experimental research involves computing the correlation between two variables. A correlation coefficient describes the strength and the direction of the relationship between two variables. The values of a correlation coefficient can range from -1, which is the strongest possible negative relationship, to +1, the strongest possible positive relationship. A value of 0 means that there is no relationship between the two variables. Positive correlation coefficients indicate that as the values of one variable increase, so do the values of the other variable. A good example of a positive correlation is the correlation between height and weight, because as height increases, weight also tends to increase. Negative correlation coefficients indicate that as the value of one variable goes up, the values of the other variable go down. In other words, the two variables move in opposite directions. An example of a negative correlation is the correlation between stressful life events and happiness. Because as stress increases, happiness tends to decrease. And this shows a brief way of evaluating the strength of the correlation, depending on the R value. Inferential statistics. As you learned in the section of this chapter on sampling, Typically, researchers sample from a population, but ultimately they want to be able to generalize their results from the sample to the whole broader population. Researchers typically want to infer what the population is like based on the sample they studied. Inferential statistics are used for that purpose. Inferential statistics allow researchers to draw conclusions about a population based on data from a sample. Inferential statistics are crucial because the effects, in other words, the differences in the means or the correlation coefficient that the researchers find in a study may be due simply to random chance variability, or they may be due to a real effect. That is, they may reflect a real relationship between variables or a real effect of an independent variable on a dependent variable. Researchers use inferential statistics to determine whether their effects are statistically significant. A statistically significant effect is one that is unlikely due to random chance, and therefore it likely represents a real effect in the population. More specifically, results that have less than a 5% chance of being due to random error are typically considered statistically significant. When an effect is statistically significant, it's appropriate to generalize the results from the sample to the population. In contrast, if inferential statistics reveal that there is more than a 5% chance that an effect could be due to chance error alone, then the researcher must conclude that the result is not statistically significant. It's important to keep in mind that statistics are probabilistic in nature. They're based on probabilities. They allow researchers to determine whether the chances are low that their results are due to random error, but they do not provide an absolute certainty. Hopefully, when we conclude that an effect is statistically significant, it is a real effect that we would find if we tested the entire population. And hopefully, when we conclude that an effect is not statistically significant, there really is no effect. If we tested the entire population, we would find no effect. So that 5% threshold is set at 5% to ensure that there's a high probability we make a correct decision and that our determination of statistical significance is an accurate reflection of reality. However, mistakes can and will be made. Specifically, two kinds of mistakes can be made. First, the researchers can make what is called a type 1 error, which is a false positive. A type 1 error is when a researcher concludes their results are statistically significant, so they're saying there is an effect in the population, when in reality, there's no real effect in the population, and that the results that they got were just due to chance. It was just a fluke that they saw that effect. When the threshold is set to 5%, which is the general convention, then the researcher has a 5% chance or less of making a type 1 error. You might wonder why researchers don't set that 5% even lower to reduce the chance of making a type 1 error. The reason is that when the chances of making a type 1 error are reduced, the chances of making a type 2 error are increased. A type 2 error is a missed opportunity. It's when a researcher concludes that the results are not statistically significant, when in reality there is a real effect in the population and they just missed detecting it. Once again, these type 2 errors are more likely to occur when the threshold is set too low. So for example, if we said, okay, 1% is the threshold instead of 5%. Type 2 errors can also occur when the sample is too small.